Is it recording? Yeah, okay. Yeah, so basically what I'm trying to say here is we have different types of switches, electronic switches and mechanical switches. But the mechanical disadvantage of the mechanical switches, they have a variant here. And we can't have it that fast switching instance as in like electronic switches. And mechanical switches also has disadvantage of if you use a mechanical switch to form a converter, how much time, what is the capacitance is needed. Like if you want to design for a boost converter, the size of capacitance will be large because the switching frequency is very less. Maybe it has a 1 hertz switching frequency or less than that. You can't expect it to do a smoother way, right? So that's a very disadvantage. So obviously we can't go for any switching, current switching, or breaking or making circuit. Mechanical switch is a kind of disadvantage for us. On the other hand, electronic switches has a faster switching response, and it also can break or make circuit with a faster response. So that gives us a better advantage in forming a converters in compared to the mechanical switch. So that led to a designing of electronic switches, and also semiconductor boost in semiconductors made this possible to break or make the circuit, right? Now, however, the electronics has been there from long back, like from half a century. But the problem with that is we can't, using the small semiconductor devices, the power handling was a challenging task because earlier days, these switches, they usually handle a very minute amount of power in watts. But later, the research and progress has taken place, and we tried to come up with a very high power handling switches, electronic switches, that we say it as power electronic switch. That we say it as power electronic switches. So in power electronic switches, there are multiple different types we have. They are classified based on the conductivity, how the current is conducted, and based on the controllability, and based on the nature of the switch, we are classified into multiple types. So if you broadly remember, what are the different types of switches you might have studied? Basically in power electronics.
Yes, yeah.
Sorry?
Bipolar switches and unipolar switches.
Yeah, basic classifications you are saying, bipolar and unipolar. So can you give me an example for bipolar and unipolar?
Bipolar, like SCR.
Bipolar is SCR.
Triax,
So
bipolar.
triac.
Bidirectional is triax. Bidirectional and directional is triac.
Okay.
Unidirectional SCR.
SCR.
Unidirectional. Yes.
Okay, that's right. So
GPO.
unidirectional is SCR and bidirectional is triac. Okay. Yeah. So before always discussing anything in details, I always have a main motivation to understand why we are studying this. As we know that there are power electronic switches. These power electronic switches generally are applied to the power systems. So what are some applications in power systems? As already someone pointed at.
Reactive power controls.
There are many applications. Obviously, reactive power is one of them. So I can broadly classify here also 3 types of applications. One, active filtering. Okay, actively you want to filter the harmonics. 2, compensations. Compensation comes like reactive power compensation or voltage, increasing the voltage profile or something else you can think of. Power conditioning. Okay, so there are 3 types of broadly can be defined. So active filters, as the name itself indicates, to filter out harmonics. Harmonics which might be created by the loads or some drives. Okay, so to filter those harmonics, we generally use it at the load points or load terminal points, so that those harmonics doesn't feed into the we're not supplied by the source. Okay, so that's one advantage. That's one of application. In compensation, you have multiple applications like to increase line power transfer capability, right? Power transfer capability by using FACT devices. Then voltage compensation. reactive power compensation. And there are many other applications. Okay. So generally we install this at the line level and we try to improve that stability, like increase the stability margins. So stability margins can also be taken care. Like power transfer capabilities comes under this category only, but I'm just writing it here. All this happens. Whereas in power conditioning, can anyone guess what is the power conditioning? Like to have a controlled power supply. Power flow through lines. Example, if you have a back-to-back HVDC converters or HVDC converters, what happens is you can control the amount of power that can be transmitted through this line, isn't it? If there are two grids are there, in these two grids there is a bilateral transaction is already there, like bilateral contract is already there, where they want to expect to share around 100 megawatt of power in a day. Every time they want to share only 100 megawatt of power. So under that conditions, you will have a better advantage if you have a controlled power flow, right? So that kind of approach can be done using back-to-back HVDC converters. Or you can also have DC power lines, even if you don't have a back-to-back converters. You can have a long HVDC lines also. So that kind of applications we use. So these are some applications. Apart from this, you already have the other applications also in drives, in loads. Major loads are also converted into polyphonic loads nowadays. So there are many other applications out there. I'm talking especially in power system perspective. Okay. And now we also got a added advantage, like sources are also fed through a converters, right? Now sources and loads are connected through converters. So our main aim is like converters that are connected to the source. We'll try to see the analysis of that, but the control of that. So that same control can also be applied for power conditioning rules also, where HVDC is there. You can also use a similar control for compensation also. The control scheme will be more or less same. It can be applied for anything. So generally, we have studied that control designing, and that can be applied as per your applications in this entire subject. Okay. Now coming to the switching. So since you know the applications now, you know that there is a future. The complete future depends on the electronic components nowadays and the controlling of those switches. So now we should focus on the switch level switches. What are the different types of switches can be applied? How they are classified? How they are used? All this can be studied now. So,
So filtering out harmonics over here. Can you brief a little bit?
Yeah, filtering of harmonics over here. Let's say you have a drive.
Yes.
So you have a drive here, machine drive. Now this is connected through a converter.
Yes.
So what does this converter does? It skews the power in such a way, in a discontinuous way or in a continuous way as per its requirement to meet the load demand. So the load demand can be anything. So while doing this process, it needs some current. The current need to be harmonious current. Okay, harmonic current is required to feed this load, to give the supply. Okay, to meet this load demand, maybe induction machine. So to meet this load demand, what happens is you want to supply some harmonic current, and that harmonic current, if I take it from a power grid, if I take it from here, what is the problem is that grid always faces the issue of harmonics, and harmonics causes multiple issues. You know, harmonic losses, and there are other multiple issues. Because of harmonics, there may be a subsequent resonance also may take place. And there are multiple issues associated with it that entirely comes into the power quality chapter again. So we are not going to there. So, but there are some ill effects associated with the harmonics when we are taking from the grid. Instead, if I have another source, okay, some active filtering with the capacitor here, if I have another converter circuit, what it is done is it feeds that additional requirement of harmonics. Okay, let's say you need a third harmonic component or a fifth harmonic component for your induction machine to 1. So the third and fifth harmonic component is supplied by here, whereas this supplies only the first fundamental component. I'm just giving you an overview. It's not the detail is very much in detail components is very much intensive there. I'm just giving a basic overview here.
Yeah. Okay.
Is that clear?
Yes,
So that's how we can design some circuitry where you can feed in the auxiliary components or harmonic components. Okay.
Yes.
Yeah. So any doubts here other than that? Okay. So now coming to the switches. So in power electronic switches, so let's talk about the classification, basic switch level classification. As so tell me, as someone said, so we have different types of switches. On a basic rule, we have based on the controllability. First is based on controllability. First is uncontrolled switch. Example.
Diode.
Diode. This is the only device which is uncontrolled, but it is most widely used device also. Okay. And second, semi-controlled. Example for semi-controlled.
SER.
SCR. Yes.
SCR.
So SCRs are the semi-controlled where you can control the power flow only in one direction, or like where you can control the turn-on circuitry. Whereas turn-off is naturally occurred by using natural commutation or line commutation, isn't it? So SCRs are such devices where you can turn on, have a capability to turn on only. Turn off doesn't depend on you. It doesn't have you can't control the turn off. Turn off cannot be done here with this SCRs. Example, SCR or thyristor, what you say sometimes. Then third one, fully controlled switches. So we have numerous number of fully controlled switches where you can control turn on and off can be controlled. Example,
MOSFET.
metal oxide, semiconductor film pillar, MOSFET, and IGBTs,
IGBT, yes, sir.
IGCTs, GTO, gate on off thyristors, right? So these are all the examples for fully controlled switches. So these are basically controlled based on controllability. We have three classifications. And what about the power handling capabilities? Based on the power handling capabilities, what is it? Not power handling, the voltage and current handling capabilities. Based on voltage or current handling capabilities. What others we have? As already someone said, unidirectional switch. Example?
Diode SCR.
Diode SER.
Yes, diodes and diodes. SCR. Okay. So why we say it as unidirectional?
The current going in only one direction.
Conduction happens only in one direction. Current Conduction happens only in one direction. Then we have another one, bidirectional switch. Examples?
Triac.
Triac.
Yeah.
MOSFET.
RCT.
MOSFET.
No, MOSFET is not a bidirectional switch. I'll say why. Triac. Others? Any other
RCT, sir.
example? RCT.
IGBT.
They are very limited.
IGBT.
Actually, to be frank, there are very limited options. So triac is one which we assume that it is bidirectional switch because it has back-to-back switches, and sometimes diac can also be considered to be bidirectional switches because diac also has a back-to-back switches. But inherently, they are not bipolar. There, you are trying to connect two diodes or two thyristors back-to-back, isn't it? Are there inherently one switch that is doing that purpose? No. So that's why there are very limited information. All these are like not exactly the bidirectional, but we can assume that it is bidirectional. But that classification, we say it as reverse conducting switch. That we say it as reverse conducting switch. Third one, which you are saying, all you are saying as MOSFET, IGBT. Okay. So actually, bidirectional switch also is not that thing. IGCT, modern IGCTs, they are still in the experimental stage. That comes into a bidirectional switch. Okay, where they have a two-side controllability and also they have this advantage. Like switch inherently has this component. Okay. Modern, I don't say this all IGBTs, but they are in the developing stage, modern IGCTs, which are yet to come. But for now, IGCTs are still in the reverse conducting switch mode, especially in the vastly available, market available IGCTs, I'm saying. They are at the reverse conducting switch. So what does this reverse conducting switch means?
There is an internal diode which will flow in the reverse direction.
Yeah. So reverse
Maybe
conducting switch. Yes, that's right. That's actually what you said is right. So they don't have internet diode. We try to connect a circuit, like we try to connect design the switch in such a way that they have an additional diode, anti-parallel diode. Okay. So
This is done explicitly, kind of.
Yeah, explicitly, yes. If these are realized, when any unipolar or unidirectional switch, the switch can be either bipolar or unipolar. What can be bipolar is like all MOSFETs, BJTs, BJT, all other things. They are connected with antiparallel diode. Unipolar or bipolar connected with antiparallel diodes. So that's why I don't want to put the triac and diac in the bidirectional switches. So triac, from this definition, you can say that triac is also like an antiparallel thyristor which has been connected to the one thyristor, right? So that's why we say it as a reverse conducting switch itself there also. No, I think triac will have a controllability. So triac can be considered as bidirectional switch. Triac is a bidirectional switch because in antiparallel diodes we don't have a controllability of a reverse side current, whereas in a triac we can have that controllability of reverse current. So, whereas diac comes under the this reverse conducting switch. Is that clear?
Yes.
So that's what the classification based on the voltage and current capabilities. Okay, these are basic understandings, and then you have all these VI characteristics of the individual switches. We are not going in that deep because it itself takes a full class, okay, full subject to discuss all the switch level importance. So let's assume that you all know the basic information. Can I assume that you might have studied most of these things in your BTech, isn't it?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, now then we will jump into directly the next topic. So these are all switch level classifications. Now, based on these switches, you form something called converters, isn't it? So we'll see some converters, like using switches. Switches connected with some passive elements to fulfill any purpose, we form a converter. Forms converters to fulfill any purpose requirements. So now, if I have some converters, if I have converters, passive elements are active switches, other switches. So it may not be only a passive elements, it can be some switches also. Now, in these converters, again, the converters are also classified into different types. So based on the source, you have AC or DC converters, source and load. AC converters, AC DC converters, DC AC converters, or DC DC converters. This is basic. I think you all studied this. You know all the examples for this, right? Examples. Can anyone say anything here?
AC cycloconverter, sir.
Yeah, cycloconverters. Then AC/DC,
Rectifiers.
Rectifiers.
rectifiers, DC/AC,
Inverters.
Inverters.
Inverter.
DC/DC.
Choppers.
Chopper.
Examples are choppers, yeah, boost converter, buck converter, all those converters. Okay, DC/DC only. And apart from, you also have some converters where we have AC, DC, AC. Examples HVDC. Isn't it? Okay, this type of converters we already have. We are already introduced with these converters. So let's not dig into this. Let's just dig into other types. Let's say there are based on type of commutation also you have one more converter types, isn't it? Based on input and output. Now this is based on commutations. What is commutation?
To turn off the SL, to turn off the any device. Turning off process.
Yeah, commutation is
Turn off
nothing
process
but
of
turn off
SCR.
process of a switch. Let's generate in a generic form, we say it as switch, not as SCR. So turn off process switch. Based on the turn off process of switch, we have commutation based different classifications. So can anyone say what are the different classifications we have? First,
A,
Classic.
B plus
yeah, okay. A, B, and all those are again in a very detailed fashion. Let me convert broadly into two categories.
Line commutator.
Lump,
Line.
commutated,
Load commutated.
converter. Example? So, first, commutated, converter. Can anyone say line commutated converter example? Okay, what does line commutated converter says? What does that mean? What do you mean by line?
Sir, natural commutation.
Yeah, that's
AC.
another name is natural commutation. Wonderful.
The source will be
So basically what we say is, if I have a sinusoidal waveform, based on the input, if the input sinusoidal waveform is reverse biased, under that condition, if the current goes to 0, it automatically naturally gets commuted because of AC nature, isn't it? You're getting my point here?
Yes.
So basically, the diode also, if you see, what happens? If diode, if it is positive, it enters, passes. If it is negative, does it pass? So here, turn and turn off process both are uncontrolled in a diode. Whereas in triac, sorry, not triac, whereas in thyristor, turn on process can be triggered by a alpha, firing angle, by firing some pulse, gated pulse. But turn off process can't be triggered or can't be avoided, like turn off process can't be created by using again any firing circle or any other things. Rather, it is created by natural zero occurrence of a sine waveform. So that's why, since it is happening naturally because of the input sine wave, so that's why we say it as natural commuted, or also line commuted because it depends on the line voltage. Like that voltage, line voltage is network voltage, phase voltage, you can say line voltage, you can say that voltage. You're getting the point there?
Yes, sir.
yes,
Yeah.
sir.
So basically, the turn off process is initiated by what? Reversal of input voltage, input AC voltage. Any doubts still here?
So means it happens naturally, like in the case of a diode, right?
Yes, it's
For
happened.
the negative half cycle.
Yes. Naturally, based on the voltage, input voltage, the process can be started. And there will be chances that it still continues to be conduction mode, even if the voltage is negative, if the current doesn't becomes naturally zero because of presence of inductance. That also happens that you see often in boost converter and other converters also, isn't it? You might have heard about this. So current should also be naturally current should come to zero also, current flowing through it. So only then it turns on. Like voltage should be negative, that is mandatory condition, and current should come to zero, isn't it? So that is about line commentary. Any doubts there?
No, sir.
Okay. Now coming to the force commutator converters, all other converters are mostly force. Most of the converters are force commutated only. So in this you have someone said there can be two processes. One is self-commutated converter. Again, you have gate turn off converter. So the one who is saying about different types of converters, where A type, D type, all these things. So those all comes under gate turn off converters, where you forcefully design like separate circuit, auxiliary turn off circuit. So sorry, this both comes under gate turn off, like auxiliary turn offs. Auxiliary gate turn off. Okay. So in the first one, inherently they have a nature of turning off based on if you have a pulse, it will turn on. If you don't have a pulse, it will turn off. Whereas auxiliary gate turn off converter means you forcefully design a converter circuit. Commutated circuit. The commutation circuit may include a capacitance or inductance or snubber circuit, whatever you say. So some capacitive circuitry, not numbers, some capacitive circuitry or inductor circuitry, where it forcefully creates some pulse or something which turns off the commutation. Is that clear what I'm trying to say here? Any doubts?
Sir, self-commutation comes under line commutated converter, no?
No. Self-commutation doesn't come under line commutation. Rather, self-commutation means IGBT. As an example, I say IGBT. What happens in IGBT? When you have a pulse, the system will on. When if they don't have a pulse, the system like the switch automatically gets off. So it is commutated selfly by the pulses itself based on the trigger value, isn't it? Level trigger, based on your level trigger, whether it is on or off, it is decided. So that's why we say it as self-commutated.
So means pulse doesn't come into play in case of line commuted.
Yes.
Because diode is an
in case
example.
of line commuted, what happens is only you generate a pulse, like you have created a pulse. After that, it is turned on. In respect of whether the pulse is there or not, that it is turned on. It will turn off only naturally by the occurrence of input voltage, negative input voltage.
Okay.
This happens naturally, whereas this is self-commuted, means it happens because of this pulse, because of the nature of the pulse.
Load computation comes under self-commutative converter, sir.
Yeah, load computation you can take under the self-commuted. Okay. So this is just, I'm just giving a basic overview. We won't use everything. Only to introduce to the subject, you should know how exactly it works and what exactly it works. Okay, that's why I'm just giving you the basic. You can say brushing off your fundamentals. That's it. Okay. Now, apart from this, especially coming to the voltage source, especially coming to the AC converters, DC to AC converters or AC to DC. Yeah, Ranjana Chaudhary, you have raised hand.
Sorry sir, वो गलती से press हो गया.
Okay. Yeah, apart from this, in especially DC to AC, AC to DC, there are two other types of converters based on the voltage and current waveforms, based on your terminal voltage. I'm trying to narrow it down to our topic. So finally, we focus on this subject. So that's why I'm trying to narrow it down. Okay. Based on the voltage and current waveform, or terminal voltage. Is my writing is legible for you? I'm just writing quickly.
Yes, sir.
Okay.
Yes, sir.
Yeah. So based on this, you have other two types of converters. One is CSC. Second one is VSC. CSC means
Current source inverter converters.
yeah, current source converter. VSC means voltage sourced converter. What do you mean by current sourced converter and voltage source converters? Can anyone have a wild guess on it?
In current source inverter or converter, the current is independent of load.
No, not exactly that thing. So in a current source converter, so in either circuit you have a DC portion, right? This DC portion is there, right? Here, what happens in current source converter is the DC side current. The DC side current always retains its polarity. Its polarity. What does it mean? In a simple language, the DC side current, either it stay always positive or either it stay always negative. So how the power transfer will take place? The power transfer takes place by changing the voltage. Either the voltage will be positive or the voltage will be negative. Then as per that, the power transfer will take place from to to or to from. Okay. So, but the current will always remain in a single polarity. Okay. You getting my point? What I'm trying to say here?
Yes, sir.
Yes, sir.
If a current wants, if I want to transmit my power to this direction, or either in this direction, DC to AC or AC to DC. So this power transfer will take place only because of the reversal of voltage polarities, not because of the current polarities. See, power is nothing but V into I. So if I want to change P to negative P, I want to change it to negative P, like power should go in the reverse direction. So under that condition, either I need to change the current direction or I need to change the voltage polarity, isn't it? So here in a CSC, I'm not worried about the voltage. Like CSC doesn't worry about the voltage, rather it worries about the current. Current polarity should remain same. So if the current polarity remains same and power transfer takes place in either direction by the reversal of the voltage, then the kind of circuitry is called voltage source converter. Sorry, current source converter. I'm sorry. I think, is it clear?
Yes, sir.
The same way, what is voltage source converter?
Voltage
So,
polarity remains constant.
yeah, DC side voltage polarity remains same. Voltage retains its polarity.
That means in case of inverter, the input side will have a constant voltage polarity. DC side means that only, right?
Yeah. Again, you need to understand here. So to understand this, let's go to the basics again. So there are two types of inverters. Rather saying inverters. One is thyristor-based inverters. One is voltage source converter-based inverters. Right? Have you heard about these terms? So one is, let's take an example. You have HVDC lines. All of you heard about HVDC lines. You might have somewhere studied about it, isn't it? In the HVDC lines, you have two types of HVDCs. One is LCC based, other one is VSC based. LCC based are nothing but thyristor based. VSC based are generally IGBT based. Generally, they can be created using MOSFETs also, but generally IGBT based. Okay. In LCC based HVDCs, they are also CSC converters. It means current source converters. Whereas VSCs are voltage source converters are voltage source. Generally, they are voltage source converters. At least the voltage polarity will remain same irrespective of either direction. How is it possible? Because of anti-parallel layers. Because of anti-parallel layers, reversal of current possible, isn't it? In VSCs especially, whereas in LCC, since there are only single thyristors, thyristor stacks, what happens is whenever you want to reverse the power flow, DC voltage polarities will change. Is that clear?
Yes, sir.
Yeah. So this is a basic example to understand where we have CSCs and where we have VSCs. So I'm just giving a basic overview here. Anything to be discussed here? Like, do you have any confusion here?
No, sir.
Okay, wonderful. So these are all basic informations which you need to know to further studies. So basically nowadays, the only problem with this and this, what is the difference? Where will you apply LCC based and where will you apply IGBT based? Can anyone say? If I want to design an HVDC, which method I'll apply? Will I apply VSC or will I apply LCC? Or else can I apply both to meet the same purpose? See, basically, just to give an overview, LCCs are applied at very high voltage and high power networks, where if you want to transmit gigawatts of power, megawatts of power, then thyristors are very effective and very friendly in nature, because although they lack a bit of controllability, but still they are very advantageous because of their power handling capabilities. So these thyristors have a good amount of power handling capabilities. Whereas VSCs, they inherently doesn't have a good amount of power handling capabilities. They are mid power range circuitry and also mid and a bit of high range, but not up to a thyristor level, but mid and a bit of high range. But switching frequency will be compromised here. Switching frequencies are a bit less. We can't go beyond certain frequencies, maybe 20 kilohertz or something around. So we can't go beyond that. And if you want a higher, very high switching frequencies, MOSFETs are there, but MOSFETs are not high power capable switches. So those MOSFETs has their own disadvantages. So Wherever you need a very high powering capabilities and high voltage capabilities, then you use thyristors based LCC based converters, whereas VSCs are used at mid-range of power handling capabilities, mid or bit of high, okay, and where you need a effective controllability, where you have a high controllability. High controllability is required. Okay, so there we use VSS. Is that clear? So our focus will be about VSS only because we need a good amount of controllability. We want both turn-on and turn-off to be controlled based on our requirements. So we will mostly study this in the entire syllabus, especially when we're dealing with AC systems, AC magnetics. Okay. Is that clear? Okay. Now let's talk about the basic configuration of VSS. So this entire subject will be focusing on mostly in AC circuit. We focus on mostly VSS. We don't talk about LCCs here. Okay. Now the bridge rectifier, bridge inverter or a single phase off bridge converter. What you say usually? How does they look like? Is you have a DC source. So there, if you want to connect to a converter, so you can directly connect to a off level switch. This is how your switch is connected. Okay. Now you take it here from the down point. But is it sufficient to work? Will it work? Can anyone say will it work? From the circuit analysis. Let's say if I turn on this, what is the voltage I see here? If I turn on switch 1, S1 and S2. If I turn on S1, V1 will be positive, VDC. And if I turn on, it will go to minus VDC. If I turn on S2. So these are all, these should be, always it should be taken care like either S1 should be on or S2 should be on. If you both, if it simultaneously on both S1 and S2, then what happens is system will get short circuited and it doesn't work obviously. So either S1 should on and S2 on. If S1 is on, we get VDC at V1. If S2 is on, we get minus VDC at V2. Sorry, at V1, sorry. Isn't it?
Yes.
Sir, minus VDC.
Yes, minus VDC if I have minus VDC. Sorry. 0, let's say. Oops, I think there is a mistake here. Yeah, I can't commit like this. Sorry. That's a mistake there. So, sorry for that. Yeah, this is a configuration. VDC by 2. And you have VDC by 2. This one is VDC by 2 and this one is also VDC by 2. Plus, minus. Yeah, now if S1 is on, it goes like this. So that is your output will be
Plus
VDC by 2. If S2 is on, what happens when S1 is off? How your circuit completes?
Yes, sir.
Like this. Sorry for that, earlier was some mistake. Yeah, it goes like this. So you see minus VDC by 2.
Minus VDC by 2.
Yeah. So previous circuit is mistakes. Sorry for that. Okay. Yeah. Is that clear now?
Yes, sir.
Yes.
Others, all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Okay. Because this is what we will use in future also. That's why please make sure that you are clarified with it. Now, this is for half wave bridge converter. Now, if I want to go with a full wave single phase bridge converter, how do I do it? Everything is same. Whether you have two switches here now. Sorry, two legs here. S1, S2, S3, and S4. So here, if S1 and S2 is on, what is V1? That is VDC. Tell me when S1 and S2 are on.
Minus VDC.
So this comes as a minus VDC. And if S3 and S4 is on, then V1 is
VDC.
Positive.
so now you have this positive VDC, isn't it? So this is how your configuration will look like. So this is for full wave. For single phase, this is for single phase. Now coming to the three phase. Instead of 2 legs, now you will have 3 legs. VDC. So you have 3 legs. So, okay, this is 3-phase system. Here you have the same DC circuit here. VDC you have. Now you have switches here. You have P terminal and N terminal. So this now you can see how you can do this switching. So this time is up now. Can you analyze this? S1, S2, and S3. Try to analyze this, okay? What happens if S1, S4 is on? What happens is any 2 switches are like upper and lower circuit, any 2 switches is on, or what happens? Any 3 switches actually we should see. So how does it work? We just try to see it. You do that? We will discuss tomorrow's class also, but in general, I'm saying you just try to analyze this thing.
Yes.
Yes, sir.
Okay. So did anyone see through this micro turbines? Last class I asked you to go through it, micro turbines. Did anyone go through it?
Yes, sir.
So what do you understood that from that?
It is a single shaft machine which a turbine, compensator, and generator are mostly mounted on the same shaft, sir.
Okay.
And the rotational speed is also very high, sir, almost 40,000 revolution per minute.
Yes, that's right.
It is more efficient than gas turbines, sir.
Yes. That's why we use micro turbines. And since rotation is very high, the frequency at which it generates is also high. So that's why we need an AC converter there.
Yes, sir.
Back-to-back you can say cyclo converter, whatever you convert, you need an AC converter where you can transform that asynchronous. Why did I say asynchronous then? Because the switching frequency, the generating frequency is something different compared to our natural frequency of 50 Hz.
Yes, sir.
So it must be more than that, right? 50 hertz.
No, not to be more than that. Okay. Yeah, so we will discuss about this full control VSA tomorrow. So once you understood this, then we will directly jump into the controllability and other aspects also. Okay.
Yes.
Okay. Then.
Yes, sir.
Yeah. So, okay then. If you don't have any doubts, we can end up this session. Any questions you have?
Thank you, sir.
Okay. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir.